Rightio. So today we're going to be looking at IPv6. So we looked at this a little when we did our Cisco course. So you may recall we went in and had a look at the different types of addresses that we've got available. We had a look at just the basic concepts of how IPv6 works. I just want to go in and sort of just go into a little bit more on that and just take another look at it. The thing about it is, of course, when we don't use it, of course, you kind of forget about it, right? So just want to go in and just take a look at IPv6, get an understanding of sort of what makes up IPv6, what the different components are, and a bit of a refresher on it. So get my PowerPoint slide to work here. That would be really good. Okay, it's decided to stop working, and I'm not too sure why that is. Come on. Let's jiggle that around a bit. Let's see what happens here. Okay, so strangely enough, my PowerPoint slide has decided it's going to stay on that page and not budge. So what I'm going to do is just dump it and start it again. And let's take a little bit of mucking around to get it where I want it. Is it going to work? Yay, now it's going to work. Beautiful. And let's just rearrange a few things here so that we can see it. All right, that's good. Okay, so here we are. It's working again. That's what we want to see. Right, I might just switch across to that view there. That's it. Okay, all good. So, working. Okay, so we're going to take a look at some of the differences between IPv4 and IPv6. I'm going to list the address types, describe IPv6 addressing format, enable an interface for IPv6 operations. So we'll take a look at the configuration of that, and configure and monitor routing for IPv6 environments. There is a section here on tunneling, which I don't particularly want to get into. Tunneling is part of IPv6, but it's kind of it's a workaround, right? It's a workaround. Like, we haven't really fully implemented IPv6. We've still got some IPv4. And how do we kind of make those things work together? There are a lot of different tunneling options. So when it comes time for you to actually do tunneling, if you ever have to do tunneling, there are like 3 or 4 possibilities that you would actually look at there, and this doesn't really cover all of them. And by that time, hopefully, you won't have to even think about tunneling. Hopefully, you'll actually have implemented IPv6 properly or completely. So let's do an introduction to it. So the protocol was defined by the Internet Engineering Task Force. It's defined in an RFC 2460, and its intention is it will replace IPv4. So interestingly enough, it hasn't. IPv4 is still alive and well. IPv6 was developed, it started being developed back in the 80s. The RFC was, let's go back and look at that RFC number here. This came out in 98. So here we are, right, 2018, 20 years later, and, there's no sign of IPv4 dying. It's alive and well. Almost everybody I know uses it. Almost every ISP that I'm aware of will give you an IPv4 address when you connect to them. So it's certainly, IPv4 is certainly alive and well, and hasn't died nearly as quickly as people thought it would. But in any case, there is an issue with the number of addresses that we have available. So IPv4 being a 32-bit address space, and here we are with the addresses. What have we got there? Well, a whole lot less than what we've got with IPv6 in any case. So go on and have a look at how many we got, but it's 2 to the 128, which is an enormous amount of addresses. In actual fact, it is 340 trillion addresses. That's how many addresses we've got with IPv6. NAT, with IPv4, NAT, network address translation, can be used and is used to extend the address space limitations. What do we mean by that? Well, as you'll be aware, we've got private addresses. I've got a private address range in IPv4, which of course is used within the internal organization or internal network addressing scheme of organizations. And we actually use NAT, or what really is PAT, or port address translation, where we are mapping all those internal addresses quite commonly to just one IPv4 routable external address. Okay, so there we have an entire network of PCs using quite commonly just one external address. Now, little note here about IPv6 saying IPv6 does not support NAT by design. Well, actually, neither did IPv4, to be quite honest with you. It was not designed to support NAT. NAT was devised as these internal addresses, but still connect to the internet using just one external address, which is kind of what NAT does for us. The thing about IPv6 is that the design team envisaged a world without NAT. Okay, they envisaged a world of IPv6 where we didn't use NAT. And why don't we use NAT? Well, because the problem that NAT solves for us in IPv4 actually just does not exist in IPv6. I mean, there are more than enough addresses for every computing device in the world to have its own unique and global address and be connected to the internet. More than enough. So we really don't need NAT. And there's a lot of, I'll just get on to this point, there's a lot of discussion about to NAT or not to NAT in IPv6. You know, and there's people will say, well, look, you've got a NAT. And why should we use NAT? So when you think about, is there any reason why we should use NAT in IPv6? Can you think of any reason, any advantage, any thing that NATing gives us that would be useful to us in an IPv6 environment? Is there anything that comes to mind? What is it?
It's safer.
It's safer. Okay. How does, in what way is it safer?
Your computer, your internal devices.
Yes.
After router, for example, where you have firewall.
Yes. Yes.
So it's more safer.
It's safer. So what you're saying is that by using NAT, we are not actually sending traffic out onto the internet which contains our internal addresses. Okay, so we are really in a way obstructing or hiding our internal addresses from the external internet, and that's true. We are, okay, and the advantage of doing that is what? Hackers. Okay, yeah. So hackers can't see our internal addresses, and that's true. That they can't see our internal addresses. And how does that help us? Well, it helps us by the fact that they can't then map our internal addressing scheme. Okay, so yes, that's an advantage. There is not this end-to-end connectivity that they can just go straight in and perhaps, contact their internal addresses. The issue is, though, that the purpose of a firewall is to prevent externally initiated sessions from connecting to internal devices. So if they know about our internal network, does that mean that they can necessarily just connect to it? It doesn't. I mean, a firewall is supposed to stop that. I understand that the less information a hacker has, the better. So in that sense, yes, there is this advantage in that they don't have our addresses. However, there are hacking tools that a hacker can use to monitor external traffic by looking at layer 4 information, TCP sequences, and other information. They can still determine the number of hosts we've got, the type of hosts that we've got. They can still determine a lot of information about our network that would enable an attack just by listening to traffic that's coming out at just the layer 4 aspects of our traffic. So there is still a lot of information a hacker can gain about our network. So the fact that they don't know our internal addressing scheme does not in and of itself prevent them from discovering a great deal of information about our internal networks, in that the type of hosts, the type of versions, the operating systems that we're running. All that information is still discoverable, and there are tools available that can provide a hacker with that kind of information. So yes, there is this advantage in that they don't have the addresses of our internal hosts. That doesn't mean that they don't know anything about us, or they can't discover anything about us. So there is that. If you really wanted to use natting to really disguise what's happening internally, there are some rather sophisticated natting devices that you can use that dynamically change the mappings and the port numbers and so on between internal and external. One of the issues is, and you're right, there is a security issue to it. One of the issues is that whatever additional complexity we add to try and disguise what's happening inside, for every sort of move we make towards that direction, we lose a certain amount of functionality within our network. For example, protocols that don't go well with natting are protocols, particularly protocols like voice over IP, SIP protocols. Don't particularly go well with natting. We can use SIP in a natted environment, but we've got to do other things to make it work, because what we've done, we've lost end-to-end connectivity because we're actually going through this natting process. So yes, there is this security around it that sort of disguises our internal network, but at the same time there's this loss of functionality, loss of performance that we kind of experience when we put natting in place. So there are pros and cons to natting. So it's not like a done deal, like yes we use natting or no we don't use natting. There's always this discussion around do we or don't we. There are some very good reasons not to use natting. The design of IPv6, from the purist point of view of the engineer designing task force, is that no, we don't use natting. We want to open up end-to-end connectivity right across the internet. But then that does bring in the fact that we are somewhat open to all of our internal addresses being very easily detected. So yeah, there is a bit of discussion around that. Let's look at this next point here. Administrators must use DHCP or static configuration to assign IP addresses to hosts, and IPv6 hosts use stateless address auto configuration to assign an IP address to themselves. So this is kind of a big change here. It's one of the biggest changes that you'll notice internally on a network. one of the goals of IPv6 is to do away with broadcasts on a network. So why would we want to do away with broadcasts? Any ideas? What's bad? What's bad about broadcasts on a network? Broadcast, well, essentially a broadcast is a one-to-all communication. So a broadcast goes to every device on the network. Every device on the network has to at least read the information that's coming in, okay? At least has to, in other words, that broadcast is addressed to every node, okay? If a broadcast goes to a switch, what happens? What happens when a broadcast hits a switch? What does the switch do with it? Yeah, so it looks at the frame, okay? Looks at the MAC address on the frame, which is going to be all Fs, okay? And it sends it out every port, okay? What does the switch do with unicast traffic? Sends it only to a specific MAC address, okay? So first of all, broadcast hits a switch, boom, dumps it out to the whole network, okay? So what we're automatically doing is we are consuming network bandwidth. So how much of a problem is broadcasting on a network? I mean, does it happen a lot, happen a little bit? Any ideas? Okay, what I suggest maybe, just as a little experiment, open up Wireshark to just open up on your computer and just monitor all the traffic that's happening on your interface. Just sit there and just look at it. Don't do anything, don't open any websites, don't do anything at all. Just sit there and look at what's happening on your interface. You'll be amazed at the amount of traffic that is going through your interface while you're just sitting there doing nothing. And you might notice a lot of that traffic, there'll be all kinds, especially in a Microsoft network, all kinds of network discovery stuff going on, all kinds of information being broadcast around constantly, and there'll be ARP requests, there'll be DHCP stuff going on, there'll be all kinds of stuff going on. All that stuff is just consuming bandwidth and not really achieving a great deal. I mean, so one of the things we want to, one of the goals is to get rid of broadcast, and of course, DHCP does use broadcasts. It has to use broadcasts because when a PC is wanting to get a IP address, what does it do? It says broadcast out and says, hey, any DHCP servers out there on the network, and that has to go everywhere. Okay, and then a DHCP server will respond, or one or more, if there's more than one, they will respond saying, they'll broadcast back and say, yep, I'm here. And then what they'll do is they'll then broadcast out an IP address as well. Then the host has to respond again with another broadcast saying, oh, I'm going to, and there might be more than one server, DHCP server, and it'll respond out again and say, oh, I have received this particular broadcast from this particular server first before the other one. Therefore, I'm going to broadcast out and say, yes, thank you. I'm going to accept your IP address allocation. That's another broadcast. Okay, so there is, and then there's a response from the server. So there's all this broadcasting that goes on. Now, you know, I put 100 PCs on a network. That's a lot of traffic, just for DHCP, get it right, alone. IPv6 doesn't do any of that. IPv6 has a completely different mechanism for assigning IP addresses, and we're going to get in. We'll take a look at that, how that works. IPv4 uses IPsec as an optional add-on, whereas with IPv6 it is built in. IPsec is built into the protocol. It's already part of it. IPv4, there's an options field in the header. It's hardly ever used, except by hackers who use it now and then, but it's hardly ever used for anything legitimate. With IPv6, that has been removed, and options and other things have been put into these things called extension headers. So the things that we only use sometimes or rarely are taken out of the standard IPv6 header, and there's the option of including them in an extension header if they need to be used. So all of that has simplified IPv6, has made it more efficient to actually use. Even though you look at it and it looks big and it looks scary and it looks awkward and it's all hexadecimal, in actual practice it is in actual fact more efficient and more streamlined. Okay, so let's take a look at the IPv6 structure here. So the header has the following improvements. Number one, it has a fixed length of 40 bytes. That is fixed. IPv4 header, you actually had to have a field in the header to say how big the header was, because it could be different depending on options and other things. So it is simple, it's more efficient as far as the way it is processed. Extension headers handle these additional options. Some fields have been removed. The header length field is removed. Why? Because you don't need it, because it's always 40 bytes, so we don't need to say how long it is. There's some identification, flags, fragment, offsets, and header checksums have been removed. So it is a total of 40 bytes. The version is 4 bytes, traffic class is 8, flow label 20, payload 16, next header 8, hop limit is 8, and then the source address, of course, 128, and destination 128. So it's a total of 40 bytes. So let's do a little comparison between the two. So you can see the IPv4 header much bigger, a lot more stuff in there. IPv6 header, nice and small. We've got the same fields are in red, so you've got the version, source and destination addresses. Fields removed in IPv6 are the orangey ones here, so they're all gone, they're all been taken out. Then we've got some that have been renamed, so we've got the traffic class is the TOS, total length, payload length, next header, and hop limit. So we've got time to live, it's called the hop limit there. We've actually got a protocol field there, which is replacing that, so that traffic class. We've got there's a new one, there's a flow label, which is a new field in IPv6. Okay, so we have these extension headers, provide faster processing, so they're just things that we don't use very often will go into these extension headers. So we've got a hop by hop, routing header, fragment header, destination options header, authentication header, and encrypted security payload header, which are added on as required. Address space, major reason for having IPv6. IPv4 address exhaustion is predicted to occur in the near future. Well, it's going to occur. We just don't know when. So how big is this? It's, well, 128-bit, 2 to the 128. So, as I said, it's 340 trillion addresses, which works out to be 2 to the 95 addresses for each person on Earth. We're not going to run out anytime soon, or 2 to the 52 addresses for each observable star in the known universe. Just to give you an idea of how big and how many addresses there are in IPv6. Okay, let's look at the address types now. We have unicast unique addresses that identify an IPv6 node. So again, this is relates to what we're used to with IPv4, standard unicast addresses. Multicast, a group of addresses, so that's one to many. Then we have, you notice that there's no broadcast address in there, doesn't exist. We have this anycast address, which is assigned to multiple interfaces and multiple nodes. Just take a bit of a look at these. Might just do an overview right here. So Anycast is a new thing that we didn't have an IPv4. An Anycast address, what that is, the traffic that is sent to an Anycast address doesn't go to all of the nodes that have an Anycast address. It just goes to the closest node that has an Anycast address. So it's a way of kind of having a group, but within the group, only one of those nodes is going to actually receive that traffic. And it's the closest one. Okay, so address notation, we'll just go and have a look at this. Every address has got 128 bits. Looks a bit scary. 816 bits hexadecimal blocks separated by colons. So we've got hexadecimal instead of our dotted decimal that we're used to with IPv4. There is an ability to abbreviate these addresses to make them look a little bit more friendly. One of the things we get to do straight up is get to omit all the leading zeros. So wherever we have a leading 0 in a hexadecimal block, we can take that leading 0 out and write it without the leading 0. We can also use a double colon to replace consecutive zeros. Leading zeros or trailing zeros. So here's an example here where we have got, first of all, we've got 3 blocks of all zeros, and then we've got one leading 0 in front of the 217. So we can get rid of the leading zeros straight away. But what we can also do is get rid of blocks of consecutive zeros. So that whole block of zeros is just replaced with 2 colons. So that makes it a lot easier. The prefix notation, we've got an RFC that actually defines that. So one of the things about IPv6 is that the host address is always 64 bits. Okay, so one of the things that we straight away don't do in IPv6 is we don't ever subnet. So you don't have to ever subnet. Why? Well, because we've got plenty of addresses. We don't need to worry about trying to subnet them to kind of conserve address space. That's not a problem at all. So basically, our host address is always a 64-bit address, and we've got the other 64 bits to make up our network number, a network address, a network prefix. We have a 64-bit prefix. Okay, so address allocation. So when you get an address allocation from an ISP, or alternatively from a regional registry, and a lot of organizations will do that. So a large organization will actually not get a provider allocated address. A large organization will actually get the regional registry or an independently allocated address. When you get this address, essentially you're going to get a 48-bit prefix. Okay, and remember that the first 64 bits make up the network number. So you've got a 48-bit prefix there. So you've got an extra 16 bits on that you get to play with and do whatever you want with for your network prefix. Small and large enterprises, same deal. You'll get a 48-bit. Very large subscribers actually get a 47-bit. So basically it's multiple 48-bit prefixes, what you end up with. Mobile networks will get 64-bit prefix, which allows multiple connections through a single prefix. And a single PC with no additional need to subnet will actually get the whole 128. Okay, so just think about this for a minute. What normally happens is when you go and get an Ethernet connection, your block of addresses will come from your ISP. Okay, so if we decide then to take that block of addresses and use that for the addressing scheme within our organization. So in other words, we give every single device within our organization a globally routable address, which is quite possible with IPv6. Okay. The difficulty occurs is what happens if we change ISPs, because our new ISP will give us a different 48-bit prefix. So then we've got to go and rename all of the PCs, or all of the routers, or everything with a static address. Basically, we've got to go and reassign numbers to anything with a static address. So in a large enterprise, the way of getting around that is you actually go to your regional registry and you apply directly for an independent assignment of your IP address. So in other words, it doesn't really matter who your ISP is. Your block of addresses that you are using in your IPv6 network are global. It's a globally routable block of addresses that you will advertise out to your ISP, and your ISP will actually advertise that block of addresses globally. So you will have global connectivity. So in other words, your block of addresses becomes part of the global internet routing table. Okay, whereas with IPv4, of course, it's private, it's hidden, it's behind the NAT. Whereas with IPv6, you have the ability to have your organization, your block, registered and become part of the global internet routing table. Okay. Okay, so special addresses, prefix 000, 000 is reserved for special addressing. Unspecified address, as we're used to in IPv4, where we have all zeros. In IPv6, that's just : : and loopback address, commonly used for testing the IP stack on local host, is just : : 1. So that equates to our 127.0.0.1 address in IPv4. Okay, we're going to get into address scope and different types of addresses. So what I might do, I might just take a very quick break right there before we dive into this, and then we'll come back and look at different types of unicast addresses and how all of that works. So let's take a short break.